Recording, that's right. Recording. Okay, great. So, so let's talk about three-phase models. So the main conclusion, roughly, is that everything that we talked about can generalize to three-phase because there's a single-phase equivalent for three-phase models. But let's just go through this a little bit more carefully. So what is a three-phase model? A simple model looks something like this. You have a three-phase source, which typically is a four-wire device. And so you have three phases. And then you have a three-phase load. So this is a simple model, at least a conceptual model to keep in mind. And the sources connected to the load by three lines, A, B, and C, phase A, B, Cs. And there could be a fourth line that's neutral at one or both ends. And the neutral lines may be connected, right? Let's say they're all grounded, for example. So this is a simple conceptual model of such a system. You have three-phase sources everywhere. Again, you could have some places have three phases, some maybe have two or one. They all be fine. It's just notationally is a little bit more cumbersome. So let's assume it's three-phase everywhere, right? Then you have three-phase source connected to three-phase loads by three lines, A, B, C, potentially with neutral, right? Now, if the lines have symmetry, and also so that, for example, also the currents are zero for all t, and the charges on each of those lines are zero, then the phases decouple, meaning that there's still electromagnetic interactions across phases, but the end-to-end behavior, let's say the voltage and the currents at the source and the load, the end-to-end behavior is as if the interaction across phases are zero, and only the self-impedance matters alone, right? So it's as if there's no interaction. Otherwise, if this is not the case, then let's say if the lines are not don't have this symmetry, and if the loads and the sources are not balanced, then you won't have this. You won't satisfy these properties. Okay. And therefore, we have to look at more carefully. How do we model a line, three-phase line, and how do we model a three-phase load, for example? So let's look at that. So three-phase line. So let's look at the picture above, right? There are four, and the big assumption, which is very reasonable assumption, is that the voltage drops and the currents are linearly related. Right? That's Ohm's law. And in this three-phase setting, it looks something like this. The V, so let's say this is node J, this is node K, right? Bus J and bus K, and there's a source or load at each node. Then the VJ A, VJ phase B, VJ C, and VJ neutral. So this is neutral, assuming there is a neutral. Otherwise, that's fine. That's just empty entry. Minus VK of phase A, B, C, and neutral. So that voltage drop vector is related to the currents on that line, IJK phase A, IJK phase B, IJK phase C, and face the neutral line, right? So if you assume it's a linear relationship, then it's a matrix, right? So the matrix is just whatever that is, and we're going to just label, I won't write down everything, but we would simply label them as ZJK corresponding to the line JK. I have a head because later on I will use another notation without head. And then the diagonal entry is AA, right? And then ZJK, this is AB, and so on. ZJK head AC, ZJK head A neutral. And similarly, this is ZBB, and so on, right? So these are just entries. We're just calling some names. Doesn't matter, right? It's not. It's just some names that we call that defines the matrix that defines the linear relationship between the current on the lines and the voltage drops. Now, what's the interpretation of these entries? Well, the interpretation is very simple. So suppose you imagine that on circuit A, you close the loop on circuit A. So it's a complete circuit on A, but don't close them on circuit B and C and neutral, right? And therefore, in that case, what do you get in the equation? Well, okay. So, sorry. Okay, so in that case, IJKA is non-zero, but all the other phases, IJK phi will be 0, phi equals B, C, and neutral, right? You just substitute in that equation. What do you get? You get this V, J, minus VK vector equals this matrix, which let's call this Z hat. And then here you get IJKA and then 0, 0, 0. Okay. And therefore, if you multiply out on the first row, you get the diagonal entry here. This diagonal entry is GJKAA is simply VJA VJK divided by IJKA, right? Because the other terms are multiplied by 0, and therefore this is the equality for the first row. Now, if you look at this, what does that mean? It means that the diagonal entry that defines our impedance, series impedance matrix, is simply the ratio of the voltage drop in phase A to the current in phase A. That's all it is, right? So it's a self-impedance in this sense. Everything involved. Oops, sorry. So this is VKA, right? Involving only the phase A. So that's the interpretation of the diagonal entry ZJKAA. Okay. These even though the currents on the other phases are 0, the current IJK in phase A induces voltage drop in other phases. So if you multiply the second row and the third rows and so on, what you get is that JK hat AB is simply VJ of B, VJ of VK of B divided by IJK of A. So the voltage drop induced by IJKA, the ratio of this voltage drop to IJKA is the off diagonal entry here. And therefore, there's there's nice physical interpretation of what each element is the ratio of the appropriate voltage drops to the appropriate current. That is the result of this electromagnetic interaction across phases. Okay, so that's the interpretation of this series impedance matrix. Now, very often in practice, typically either the neutral line is absent. Let's say if you have delta low or delta sources, then there's no neutral line, or both the neutral lines are at the sending and receiving end and grounded. Now, in those cases, then ijk n equals 0, if there's no neutral line, we just set ijk n equals 0 for in this equation, in this equation, right? In the second case, if both ends are grounded, then we get Vjn equals Vkn. Now, if you substitute this, one of these two conditions in that basic relationship, then you get a nice simplification. In the case when there's no neutral line, so ijkn, which is, this is 0, okay, then we can ignore the last and row and last column and end up with a relationship between ABC phase and ABC phase on the current, related by 3x3 matrix, right? It just involves this matrix. In the second case, when Vjn equals Vkn, so both ends are grounded, for example, then this difference is 0. So you get a 0 at this entry. And therefore, you can express ijkn in terms of the other currents, right? So you get, more specifically, you get ijkn equals minus of zjknn, the diagonal entry and the neutral line, zjkna ijk right, that one is the same, jk and c ijk c. And therefore, if you substitute this expression back into the other equations, then you get a relationship between just the three phases, Vj, Vj, ABC minus Vk, ABC equals to some 3x3 matrix. Let's call this GJK AA, CJK AB, CJK AC, and so on. BB and CC. Right? And then the phase currents only. Okay, so this is what we will be dealing with most. So we call it small zk, which is 3x3 matrix. And this is the phase impedance matrix and series phase impedance matrix, only the series part. Now, you could add, and therefore in vector form, this looks very much like before. We just have Vj minus Vk equals Zjk ijk. In single phase, each symbol is a scalar. Here, they are either three-dimensional vector or 3x3 matrix. That's all, right? And this is only the series impedance. If you add, and also this zk in practice, because the properties of the lines and everything has very nice properties. Typically, under reasonable practical assumptions, this zjk is invertible. So you can talk about admittance matrix of this 3x3 line, 3x3 admittance matrix, and some other symmetry properties and so on. And if you want to add shunt admittance, then you would just look like this. That you look at ijk, which is a three-dimensional vector, is yjk of s, where yjk of s is the inverse of that, jk inverse, okay? The series impedance inverse, times Vj minus Vk, the three-dimensional vector, plus some other matrix, 3x3 matrix, this. So this is the equation for three-phase unbalanced system with shunt admittance that models the three-phase line, okay? So that's the three-phase line model. So am I running? Oh, sorry. Okay, sorry, I need to spend too much time. Okay, let me just say the low, okay, impedance low in Y configuration. Okay, Then again, you draw the diagram, you write down your Kirchhoff laws and all of that, you get a relationship that looks like. So impedance low looks like this. You have a three-phase line, as we saw before, A, B, C, and then there a potentially neutral, right, which is grounded. And then you have internally Y configuration. Then you get V equals ZY of I, where V are the voltages, VA, VB, VC, VC, and currents are IA, IB, IC. So they are related by a matrix that defines your impedance low. Now, for if your low is in delta configuration, unfortunately, I think maybe if you're interested, you should look at the notes. I won't have time to go through the detail, but you will end up, if you go through the writings and so on, you will get the relationship between the terminal voltages on the three phases and the current to look like, let me give you one example, something like this. Minus CA minus EC.
Professor Steven, your audio is, excuse me, your audio is very weird.
You mean the connection is bad? Is that?
Now it's better. Now it's better. Great.
Okay.
I couldn't hear you before. Now it's okay.
Okay. I can switch to a backup if that happens again. Let me know.
Yeah, I'll let you know. Yeah.
Okay.
You can continue. Sorry.
And it's symmetric. So you will look something like this, where ZA, ZB, and ZC are the impedance of the low in each phase. So the impedance of each phase, they will compose in this manner into a phase admittance matrix that defines the relationship between V and I. So this is how we model three-phase components. Now, what happens when we have a network? So it's very simple. Unfortunately, I think I will skip the details. The details are all in the notes. But what it ends up is that you will have, if you identify, there's a single phase equivalent, where if there are n nodes in the original network, then there are 3 n nodes in the single phase equivalent, one for each phase. And there will be a admittance matrix, the global admittance matrix, that will be defined by the constituent admittance. So those small YJKs that we saw earlier, one for each. Each YJK is a 3x3. They will compose this big admittance matrix. One example of this is that if you have 3 nodes, so this is Y13, so node 1, 2, and 3. This is Y23. Each Y13, Y23 is a 3x3 matrix. Okay, then your Y matrix for the entire single phase equivalent will look like this. There's a Y13, sorry, there's a Y13 3x3 matrix block minus Y13 3x3 matrix, and then minus Y23, Y23. And this is Y13 plus Y23 minus Y13 minus Y23. So each of these blocks is a 3x3. And you satisfy the properties of admittance matrix, say the sum, the row sums are 0, column sums are 0, and all of that. And therefore, you can think of this as the admittance matrix of the single phase equivalent. Then everything we talked about so far applies to this single phase equivalent circuit. That's the way to deal with one way to deal with the 3-phase unbalanced network. Unfortunately, now we have 4 minutes. Okay, so in a couple minutes, so what can I say about? Okay, 4 minutes. Let me just details are in the notes, so it's on Canvas. But let me just give a high level this quadratic convex relaxation. What is this about relaxation? The main thing is that it uses polar form. So the semi-definite relaxation we'll be talking about, we can derive it using the complex form. If you use a polar form powerful equation, you can also derive this quadratic convex relaxation, which is not dominated by SDP relaxation, and it does not dominate SDP relaxation. So it is another relaxation which can be better or tighter or not as tight, depending on the problem, the SDP, and therefore it's a valuable relaxation. So what the main idea in that is that if you look at the polar form equation, so let me finish in 2 minutes. So the polar form equation, it looks like this here. So the key idea is if you look at the line flow, real line power line flow, PJK, it looks something like this. VJ, VK, cosine theta JK. So where are the nonlinearity? There's a, let's say, think of this as xj squared. This is xj, xk. So xi's are all real, okay? So this is quadratic term. This is a quadratic term. And then there's a cosine. That's nonlinear, cosine theta. And then there's a sine theta. As a constraint for your OPF, it means that your power flow solution or your optimization variable needs to lie on these nonlinear lines. So, for example, if x squared, then this defines your feasible set. It has to be on that line, right? If it is bilinear, it looks it's harder to draw. You can still draw it in 3D, but it's some surface, nonlinear surface. And if it is sine cosine, if it's cosine, let's say it's this, right, with a certain bound. If it's sine, it looks something like this. Oops. Right, so with a certain bound. So these are nonlinear lines that defines your feasible set. That's non-convex. So what do you do? Well, the idea of quadratic convex relaxation is that the key observation is that the x always have bounds. Oops. Okay, so these are the bounds on your x. And therefore, I will, instead of having the line to my feasible set, I'm going to use a convex envelope. So for quadratic, it looks like this. Okay, let me blow up the quadratic, and that's the idea. So this is your feasible set, the quadratic within a certain bound. And instead of using this as my feasible set, the line, I'm going to use my feasible set as this. So I allow my variables to be any point in that brown region, which is the convex set. That's the idea. And therefore, the relaxation is to relax the curve, the graph of the graph into a set that contains the graph. That's all. That's the idea. And therefore, if I know the bound, the lower bound and the upper bound, I know the equation x squared, I can easily figure out what is this line and therefore what is this region. Similarly, for cosine, I know the bound here. I'm going to use this is my feasible set. Instead of that line, this is the my feasible set. And for sine, what I'm going to do is I'm going to take the, so this is my feasible set. It's basically two lines that touch the curve, the sine curve, at appropriate points within this bound, right? And you can figure out exactly where the touch points are, and therefore what the lines are. And those lines defines the convex region, convex superset. And then there's a bilinear term, which is harder to draw. It's in the nose in 3D, but you can also get a convex hull for your bilinear surface. And this is a first idea in quadratic convex relaxation. The second idea is to use composition. So if you have this bilinear term multiplied by another nonlinear thing, right? So this. Then for each of them, you can relax it to the convex hull or convex region, convex superset, and their product you can compose. You can apply the same idea to their product. It's a bilinear term, and therefore through composition you can relax this entire graph into a convex superset, and that's your quadratic convex relaxation. So that's the high-level idea, the details in the notes, and also in the original papers. I apologize for running over for a few minutes. Yes, so I will try to answer some of the questions that's posed. Thank you very much, and I'll see you tomorrow. And then, of course, there's 3 days for the entire week that will talk about other aspects of advanced modeling for distribution systems. Okay, thank you very much. I'll stop the recording.